All right, good morning. Again, my name is Craig Hofmeister. My co-presenter, Steve Hill. Both of us are from Rolf, Jensen and Associates. I think the intent of our talk this morning was to kind of get things moving in a general direction. We're going to talk about using the new SFPE guidelines for substantiating a fire model for a given application. As I mentioned, I think the guidelines are relatively new. They were officially published earlier this year. And our intent is Steve and I are going to go through the framework and the methodology for an actual project application. It is a project that happened 5-6 years ago. So in effect, we're kind of going through the process after the fact. The guidelines and the methodology was not available at the time. But both Steve and I served on the task group for SFPE, as did a number of people that are here. I think we had a real nice well-rounded task group with representation from kind of the users and the consultants in our standpoint. We had model developers, we had AHJs, and so I think we had a good, like I said, well-rounded representation that brought their different perspectives and views to the group. The intent, and this will be speaking solely from my standpoint, I guess, the intent of the guide is really to provide model users and any stakeholders, owners, AHJs, a way to systematically look and see, is the model that I've chosen or the model that I think I want to use appropriate for the application that I want to use it for. So certainly it brings in things like V&V, verification, validation, and so forth, which we'll go through. The project that we're going to go through, like I said, it's a performing arts center atrium. So I think in the overall grand scheme of things, it's a relatively simple example dealing with smoke movement, but it does have some unique aspects to it which may drive a model choice. Like I said, it's a performing arts center atrium, and so the atrium space itself, well, there's a picture of it from the outside. It is built at this point. What we're looking at here is kind of the back side of the building, although it's the lobby area. The Performing Arts Center, the actual theater space, is on the opposite side of the building. So this 3-story space provides a circulation to get into the balcony tiered seating and all the seating for the actual theater space. So simply just from a circulation standpoint or a building use standpoint, ended up with a 3-story atrium, and which was what was driving the use or the idea that we needed to use a model for smoke movement, smoke exhaust. Here's a picture of a cross-section of the atrium itself. Certainly this is not something that we would normally have during the design. I'm going to talk about some of the design aspects in a minute, but the idea here is just to give you an idea of what the space looks like. Relatively narrow, open space, and it's really just open stairs, open elevators, and so forth that get you up to the various levels to get to the theater and the seating space. The picture on the right is just a floor plan. It's hard to see a little bit, I guess, but some of the darker grayed areas. Try that. There we go. Some of the darker grayed areas here would be the open atrium space. It is fully separated from the seating area as it goes out to the stages down in this area. So this would be floor area on one of the upper levels. This is all open space, kind of a unique design, open stairs. And I guess the hitch in this as to why it was a little bit different than a typical box or cube atrium is it has to wrap around, the atrium space actually wraps around the seating a bit. So it's not shown here in gray, but these side stairs are all open to the atrium space. And so we got a lot of these narrow pockets, corridors, and spaces that certainly make smoke control a bit difficult if we're dealing with how we're going to make sure we get effective smoke control, allowing people to circulate or use the space in their egress paths. So the methodology guide itself, I'm not going to spend a whole lot of time on this. I assume that most people are at least somewhat familiar. Like I said, it's relatively new. It was published earlier this year. I'm sure it's not the perfect solution, but it is what has come to this point. And it really provides a systematic approach to review your application. Certainly on the right, we've got it's set up in 5 chapters, really, 6, I guess, if you count the introduction. But goes through, define the problem of interest, select a candidate model, verification and validation, user effects, and documentation. I think the idea of the task group as we were going through was to really develop the guide in such a framework where you would go beginning to end, and at the end of the day, you would have some type of documentation to say, I went through the process, this is why I chose the model, or this is why my model didn't work, maybe I had to start over again. And on the left is kind of the flow chart, which I'll again go through very quickly. So as we go through the flow chart in the beginning, you would define what your problem is. And again, we're going to go through this for the case study here in a second. Select your candidate model. Does a candidate model exist for the use that you're trying to use? If no, can you redefine the problem? If you would, then you would have to start over again. If not, you basically would have to require model development, perhaps some testing, some other means to try to establish why you're using that model. If we do have a candidate or multiple candidates exist, then you go through the verification and validation. Is a model suitable? If not, you have to go back sort of to the beginning and select another model. If it is suitable, then you would go through perform the analysis, evaluate uncertainty, user effects, and certainly the documentation. So I think the idea here is we'll go through this more in a general sense for this case study. So in looking at that, we know that we're going through, we have an atrium smoke control problem effectively. There's certainly been lots of work on atrium smoke control, both using models, using hand calculations. There's actually been a fair amount of testing and so forth. So it's a relatively well-defined area of our work. But going through in the beginning, what is the problem? I think we're going to need to look at smoke production, smoke movement. Certainly we might have mechanical exhaust. It might be passive exhaust or passive venting. We might have mechanical or passive makeup air. And then certainly as we go through, it's a good idea always at this point to look at what other previous work has been done. Like I said, there is quite a bit of work in this area, both from a research standpoint and from a use standpoint. The next piece, which is I think one of the more important pieces of the guide to go through this methodology, is what are the key physics? And I think we talked about this in the task group for quite a long time. In some sense, it's relatively simple, but it's something that's probably often overlooked as we go through this kind of the process. Some of it is because there has been so much atrium smoke control done over the last 20 to 30 years. But as we go through the key physics, certainly we'll go through, we have smoke movement, we have smoke temperature, smoke concentration, smoke layers, compartment pressures, ventilation, visibility. Those are certainly direct things that we may need to account for in the model. Then there's some other things that may play a part, whether you take into account in the model you're trying to use, whether you do this in a separate analysis or whether you use a separate model, things like heat release rate, flame height, heat flux, ceiling jet, and sprinkler detector responses. So again, I think it's just a real good idea to clearly define these, make a list. What are you actually trying to accomplish with your model application, and start from there. And then as you move in to what some of the other parameters might be. In our case, it's during the design, so we have a lot of information, but you never have all the information. Our geometry is relatively well defined. The architect has a vision. That kind of configuration that you saw was established pretty early on in the project. From a frustrating standpoint, from a consultant standpoint, is that often changes partway through the project, and then you got to decide, does that, if I already have gone through the model analysis, does that invalidate it? Do I got to start over again? How does that play into it? But for the most part, it's relatively well defined. Timeline. Certainly, you really have two basic choices here. It's either a transient timeline or it's a steady state. In our case, depending on the model that we might want to use or the model we might choose, it could be either one. Certainly, hand calculations or correlations are primarily steady state. If we're going to actually use a more sophisticated model, a zone model or a CFD model, it's usually going to be a transient type of analysis. And so while we don't want to have preconceived notions necessarily going in, usually as a user you have a pretty good idea of what model you want to use and what pieces and parts that you're going to need to consider going into it. Events, certainly there's fire growth and smoke or fire detection, how you're initiating your smoke exhaust, how you're initiating your makeup air, and then some other things that may play into a part. Is there, I'll get into in a second, but materials. Obviously, I've got lots of question marks in materials. This is probably perhaps the hardest piece in a design standpoint. Usually we're doing this type of analysis fairly early on in design because it's a big piece of how we're going to establish the smoke control. Has an impact on where the mechanical is going to put their vents, their fans, all sorts of things that could impact the actual design of the building. When we talk about smoke control, experience tells us that it's usually not about the exhaust. You can put as big of fans as you want on the roof for the most part. That's not the big issue. It's the makeup air. How are we going to get effective makeup air into the space at relatively slow speeds, which is required by codes, and we don't want to impact the smoke plume, the fire plume, and so forth. And so it can have a rather large impact on the design of the building. So when we get back to materials, I'll talk about this again in a second, but we don't know. We can make some assumptions, and Steve's going to talk about user effects and uncertainties and so forth, which is a big piece, but trying to predict the use of the space in the future. And that could be anything from acoustics, materials, which is something that was very important in this project. This was a Class A theater space, which really means had to deal with traveling Broadway shows. Class A is kind of the highest level of performing arts center spaces, at least as they define it. I learned way more about acoustics than I ever wanted to know as part of this project. But certainly those materials are different than we might find in a more traditional office building or other type of building. And what impact are they going to have on the model? So we need to consider it at this point, but there's a lot of unknown that we'll need to think about. And then certainly there's other boundary conditions. What's interior temperatures, outside temperatures? Is that going to have an impact on the analysis? Fan vent status, HVAC, regular HVAC for the building, wind, and so forth. So at the end of this define the problem of interest section, it's really then to go through and redefine what are you really trying to use the model for, trying to clearly define what we want to use it for. In this case, smoke layer analysis or attendability analysis, and that kind of depends on the model that we would choose at the end of the day. You could certainly go into this in a little more detail. I want to know what a temperature is at 6 feet above the third floor, for an example, if you wanted to really get into more specifics of your define the problem. So I'm going to take a little side shoot here. So the other considerations, I talked about materials, and I can't express this enough. It's probably the biggest piece of trying to do this analysis is the user effects or some of the uncertainties. We simply don't know how someone's going to use this building from 20, 30 years from now. And that's the hardest part in trying to go through this, and it goes into how we choose the model that we're going to choose. And this is just a couple of quick examples. The one on the left is a football stadium. So this is a domed football stadium. When we first got involved in the project, I said, well, what kind of uses are we going to have? And the answer was, well, it's a football stadium. So it's football and then some small events, nothing very significant. Followed up with a question, well, can you send me some pictures or do you have better descriptions of what kind of events? Lo and behold, we come back and now we have concerts and we've got rings of RVs and all sorts of things. Obviously, that's going to have a huge impact on what we're choosing as a design flyer and so forth. What types of materials that we would then be considering in the model and what kind of flows and so forth, which may drive some of the model choices. Certainly this is a mall on the right, and this is a little more typical. I think we've all been in malls where they're displaying a car or a boat or something along those lines, and that's not too surprising. I've rarely been in a mall where it's a full-blown car show, where it's not one or two in select places, but it's 40 or 50 cars, which again certainly is going to impact how we're going about the model choice. So back onto the SFPE guide, a little more straight track. So as we get into, we've defined what our key physics are. We've looked at what our model objectives are, our analysis objectives are, and we'll go through, well, what types of models are available. There's really three basic. It's either the algebraic correlations, calculations, a zone or a lump parameter model, and then a field or a CFD model. And while it's not a category on its own, you may use a combination of these models to end of day get your answer. So again, back to our specific application, we're looking at what our input or output considerations are. I think we knew going in that while it's a smoke control application and we could use a smoke control, any of the three, either algebraic or a zone or a CFD model, we had an idea going in that the relatively strange geometry, we had lots of obstructions to smoke flow, it was more than just a regular cubed atrium. We probably were outside the bounds of the algebraic equations, or at least of what they were tested to way back when. Similarly, the zone models are often based on the algebraic equations, and so we had an idea going in that we probably need to get into a CFD or a field model, and so that drove some of the input and output considerations. And again, at the end of the day, it was really a difference between, are we looking at a smoke layer analysis, which would really be a zone model, or we could use a zone model or algebraic equations, or are we getting into tenability, which was primarily going to drive us to a more sophisticated field model. At this point, again, we're still at the select a candidate model phase. There are other considerations. Certainly available resources. Now, this should not drive it, and by available resources, I think we've even mentioned it in the guide. We might be talking about computer resources. It might be personnel resources. While that shouldn't drive the end-of-day choice of the model, it is a consideration. If you decide that you've got to do 100 model runs or model simulations because to adequately address your uncertainties, if you're going to use a model like FDS or another field model, that's a significant amount of time. Maybe those runs or simulations take 2-3 days apiece. Do you really have that kind of time to do this kind of project? Or a lot of times it's going back to the architect and saying, this is what we need. I know you want the answer in 2 weeks, but it's just not going to happen. And again, sometimes that could drive the choice of the model, or at least play a part, maybe not drive the choice of the model. And that gets into how are you handling your conservatisms, your bounding, your sensitivities, and Steve will talk about that again in a minute. And again, not necessarily a technical aspect, but it can have a big impact on the success of the model, I guess, from our standpoint, from a user, is the graphics and the presentation. It goes a long way to help AHJs or other stakeholders to understand what we're talking about in the analysis and be able to clearly communicate the information that we're trying to get across. So, just simply having that graphics piece, while it's not the technical aspect of the analysis, it does go a long way to conveying and communicating the results of the analysis. So with that, I'm going to let Steve talk about the harder parts of verification and validation.
Thank you. Thanks, Craig. So once the candidate model is selected, the next step to find in the process in the engineering guide is, is the model that you've chosen, does the predictive capability of that model work for the certain application you're looking for? In other words, is the sorry, hold on for a second. Right, sorry. The predictive capability of the model needs to be assessed. So is it appropriate for its intended use? Now, Craig went through all the uses a few minutes ago in terms of, here's the reasons why we wanted to use a model. So we really have to go through at that point in time. With any of these, any project you're taking on, you need to make sure that the V&V process is adhered to. So the engineering guide goes into a lot of detail in regards to verification and validation. And those can be scary words for a user because a lot of times the model developer is really ingrained into the V&V process. And so the distinction we need to make here between the model user's responsibilities and the model developer's responsibilities are fairly significant. And the engineering guide does go into the details and what the differences are, but it's really the responsibility of the model user to select the model and then make sure that it's also appropriate for, wrong button, it's also appropriate for the actual application of interest. Now, the model developers are essentially tasked when they perform a V&V study on their particular program to make sure the mathematics of the models are correct, to make sure that the equations that they're using to define the physics have been implemented properly. And there's a whole other set of standards, and an example of that would be the ASTM E1355 standards documents, which outline methods for that. So while that's referenced in the engineering guide, that's something that's not specifically really the user's responsibility. However, the user does have a responsibility to make sure that the model is going to function as it is intended to make sure the physics of the model are appropriately defining the problem of interest, make sure the parameters, the input parameters, there it is, to make sure the input parameters that are used with the model, the choice of your model are actually appropriate for the application. To make sure that the range of your parameters are indeed valid input parameters as well. And the results need to be gauged in regards to, are the results really meaningful? And are they not only meaningful, but are they also within the bounds of uncertainty that is acceptable? So the verification process, again, focuses more on the mathematics. The validation process is the process that says, okay, you have a model now. Is this model really going to give you meaningful results, and are they going to be within the bounds of certainty? And if they're not going to be within the bounds of certainty, is it something you can qualify instead of quantifying? And so you actually have a good sense for whether or not the results are valid for your intended use. the main point here is that the validation process is something that is typically not done by a user in regards to the actual test data. A lot of data that's out there is experimental data or other V&V studies that have been performed, and existing validation studies can be useful to modelers. However, if the data that's out there does not conform to the problem of interest and the application at hand, it's very possible that someone might have to either commission fire tests to generate the data that can be compared to the predictions, or maybe there's existing data out there that needs to be analyzed further. But in general, I skipped over this part, the process and how you validate, you're comparing between the predictions and the measured predictions of your model and the experimental test data. So the idea is that if you can get a sense for how different the results are from the measured experiment versus the predictions, then you have a good sense for how valid your data is. So this is a process it's not well defined in regards to how users need to deal with it, but it's very well defined, I believe, in the engineering guide as something that needs to be considered. For the purpose of the Performing Arts Center, the FDS model was chosen. As Craig said, it was actually selected as the candidate model, but we still haven't gotten through the flow chart he showed, so we still haven't gotten to the point where we've actually chosen this model to be appropriate. So, but going into it, knowing we're going to be using FDS, there is an existing case study for a V&V study that exists that was performed in part by, or jointly, that is, by the Nuclear Regulatory Commission and the Electric Power Research Institute. And it's available in the document New Reg 1824. It was specifically performed for applications in nuclear power plants, but there is a number of fire modeling parameters here on the next page, we'll get to in a second, that were actually looked at with the study. Let me jump back here real quick. I should say this is a several volume document, and the first volume is an overview summary, but if you look very carefully here, they do go through and they've validated, or they've done a V&V study on both calculations in terms of fire dynamics tools, which the Nuclear Regulatory Commission has put out there, the 5 Revision 1 model as well for PAN calculations. Then 2-zone fire models are also covered in a separate volume, and FDS has its own separate volume that goes into detail in regards to the comparison of these measured parameters to 6 specific fire tests that were utilized for the comparison. So of interest in the atrium scenario, as Craig mentioned earlier, are tenability criteria that involve hot gas layer temperature, also tenability of the visibility aspect of the tenability. So the smoke concentration or soot aspect of the model prediction is of interest, as well as the species concentrations. So here we talk about oxygen concentrations and carbon dioxide concentrations, and we're looking at species concentrations in the model as one of the tenability criteria specifically. And of course, all the tenability criteria that we chose to compare to need to be run by the stakeholders in advance, so everybody's on the same page in regards to this particular project. So these are all chosen in advance, but we did not choose to go into looking at ceiling jet temperatures specifically, or the impact of a fire having a secondary item ignition. So flame spread wasn't an issue, or radiant heat flux to targets was not an application that we needed to worry about in regards to verifying and validating. Now, in the FDS, in volume 7 of the New Reg document, the FDS study compares 6 fire experiments and all those applications I showed you on the page beforehand. And there's a ranking criteria. So first of all, to figure out if the results are valid, this particular document takes a look at the first question: are the physics of the model appropriately described by the calculation? Is that piece accurate? And if it is, the next criteria ranking is, do the model results differ significantly from that of the measured data? Now, in this document, I thought it was very well presented, and it shows that if both of those criteria are satisfied, you get a green light. You can go ahead and, for the most part, there's a high confidence level that the model is suitable for the application of interest. If the ranking comes out as yellow, it's a caution assigned to the user, that the physics are properly described. However, not all the experimental data matches up with the predicted measurements. Now, the fact that that might be the case doesn't mean that the end user can't use it. In fact, a lot of this application of the engineering guide is a level of engineering judgment that needs to be applied. In the case of, oh, by the way, so if it's red, obviously neither criteria is satisfied, and then therefore the model should not be used. But in regards to the yellow ranking here, I wanted to say it doesn't mean you shouldn't use it, because in the case of our particular application with the Performing Arts Center, both the hot gas layer temperature and the smoke concentration predictions, we have a high confidence level that they are actually valid results at that point in time. FDS is definitely applicable and an appropriate model to be looking at the transport of smoke through adjoining spaces, and that's what the comparison of the measured data to the predictions showed. And for species concentrations, however, though, actually I believe species concentration should be green. I apologize. I think I messed up those colors. I know I did, because smoke concentration is, that was the yellow one ultimately. And the reason that is because only one of the 6 test series was actually focused on taking soot measurements. And at the end of the day, the comparison of the results here showed that there was a 600% increase in soot concentration in the experimental values. So there's an over-prediction of soot concentration in the model as compared to the experiment, which we decided in applying the FDS model to our problem of interest is a conservative result. And so because it's a conservative result, it doesn't really negatively impact the design aspect of this. So once the model has been validated and verified, and the user has a good understanding that it's appropriate to use and the results will be meaningful, the next step is, in the flow chart that Craig showed, is to examine the user effects. Now, arguably, the user effects provide the largest source of uncertainty in a model. And oftentimes, they're a little harder to quantify. So if you can't quantify them, you should at least be able to qualify how your input parameters or your spatial domain or other types of input assumptions actually affect your results. It is the user's responsibility to make sure that the parameters you use are indeed appropriate, and if there's some type of bounding analysis or sensitivity analysis that needs to be done, that's really on the user's shoulders to make sure that you're within the realm of appropriateness for the equations that are being used. You really should have an understanding of the impact on the model output. So if there is a 30% increase in your heat release rate, you should have a good understanding on how that actually is going to affect a multitude of things in the model you're actually using, for instance. In the case study at hand, the spatial domain, as Craig said, was relatively well defined. However, there still is things that the user has to make sure make sense in terms of carving out the space and building your model in FDS in terms of meshes. You have to make sure that it's appropriate and that the grid cell sizes line up appropriately, obviously, or else the model won't work. But beyond that, you need to take into consideration, keeping some of the physics of the fire plume away from the boundary, for instance, of some of the grid cell boundaries from the meshes. That's an important thing to do. So the physical space, the consideration of that is important. And Craig mentioned the resource limitations. Obviously, if you want to try to run a model that has very, very small grids to get a finer level of resolution, then that's something that you might not be able to afford, either in terms of computational time or just the number of computers you have to run the model. For the purpose of the Performing Arts Center, a grid resolution study was performed, and at the end of the day, the grid size was selected initially based on the general guidelines that are provided in the user's guide for FDS to get a sense for are we optimizing the use of the grids here. But aside from that, the resolution study showed that the ultimate grid cell we ended up with, which I believe was on the order of about 1.5 feet by 1.5 feet by 1 foot tall, ultimately was appropriate for the model, and that varying that grid size did not impact the model output significantly. The definition of the fire is really one of the biggest things that clearly affects the production of smoke or the transport of heat throughout the space. So you really have to take into consideration up front, is the fire size appropriate? And as Craig said, there's a lot of different considerations that you have to take account of, and as the stakeholders agree on the correct fire size, that's only one aspect of it. Then there's the fire growth aspect of it. So all those parameters need to be defined. As a user, you have to understand that that's implemented into the model correctly, obviously, and also the impact that has if you, for some reason, don't do that. Now, there's impacts that are less obvious to the inexperienced user, such as, well, there's an intentional impact that you might want to put in place, and that would be the effect of suppression on a fire. And that is obviously, going into this study, we did not look at that as being one of the key physics that we had to validate, because we were not considering that sprinklers would have an effect on the suppression using FDS. In fact, what was done was a different model, DTACT specifically, was used to conservatively predict the sprinkler activation time as a standalone process. And so it should be noted that when you use other types of programs like DTACT or any other calculation or two-zone model to supplement the input parameters of your calculations, or the input parameters for your model, that they should also be vetted through a similar process like this whole engineering guide is structured for the FDS use here. But we did use DTACT in our case, so we did take into account the effect of suppression, and we believe it was a conservative effect. So while we're not specifically quantifying the effect, it is qualified in the sense that we know we're predicting the sprinkler activation a little bit longer into the fire as it would have otherwise had the walls constrained the hot gas layer, for instance, and it would have activated sooner in the actual model if we took a look at that. Unintentional impacts that the user needs to be considered of as well are that of ventilation. Now, for the atrium model, where there's typically a good amount of ventilation and there's no effects of or there's no ill effects of ventilation, I should say, on the actual fire, the heat release rate that you've input typically is going to be output and produced. So that's something to consider. If you don't include makeup air, for instance, you might not get the actual heat release rate you wanted. So those effects are certainly something that can cause uncertainty, and if you're not aware of that as a user, you need to make sure you are. The fire location is another source of uncertainty and error, possibly. In the case of our model that we ran, both axisymmetric and balcony spill plume models were considered. And it's hard to see in the graphic there, but this is an axisymmetric plume where this is the entry-level orchestra level, and then there's the mezzanine level. On the orchestra level, there was a fire out in the open that was the axisymmetric plume, and then there's a fire underneath the balcony on the entry level, which was our balcony spill plume condition there. For spatial concerns, with the fire location, if you place the fire on a boundary, you might get some ill effects that you weren't considering, and also if you don't define your grid or if you find your grid in the area where your fire is located differently than other spaces, you may have good reason to, you may have unintentionally done that, but the idea is that you need to make sure you have a good understanding of where your fire is actually located, and the grid cells associated with that they're not going to provide negative effects of the smoke production. For surface properties of the space, that also impacts things as well. In our case, we made a decision to take a look at all the materials as being inert, and that was something that was done in an attempt to make things a little more conservative on the output, because we're not losing heat to the outside. We're essentially keeping the heat in the atrium, and therefore causing potentially a worse or a severe case scenario for the occupants. We were not looking at any secondary item ignition, so the thermal properties of the walls as being inert were considered to be okay from that regard. Flame spread was not an issue. We're not looking at the transfer of fire from one material to another, so the inert assumption held up for us, and it was deemed appropriate. From the measurement side of the house, as Craig said, we're taking a look at, from the performance-based design standpoint, temperatures, soot concentrations, and species concentrations at specific points in time and at specific levels throughout the atrium in this very convoluted space. So one thing we have to take a look at were how we're going to view them, and obviously simple graphs are effective. We did use the companion software program SmokeView to take a look at the results as well. So we did look at slice files, we looked at ISO surfaces. So we combined point locations versus average value locations, or average value results, that is, and made sure that we weren't missing the fact that maybe the smoke layer descended in a certain area that we didn't have a specific device at. So the slice file and the ISO surfaces were certainly helpful from that regard. So there was powerful tools within SmokeView that helped us view the results from FDS to make sure that the measurements we were looking for were indeed the measurements we were reporting. And then also the frequency of the results we were looking at is also of interest. Are we looking at a threshold value or some average value as well? Safety factors we also took into account, and in general the scheme we took was we tended to add up the safety factors and never quantified them, but knew we erred on the side of conservatism in most of the things we did. Now the documentation aspect, beyond the user effects, once you document them once you've assessed the user effects and understood the uncertainty you're dealing with, the documentation step is something you really shouldn't forget to do. It's really a self-documenting process if you follow the guide. And it was structured with a purpose, as I say here, and there's a logical progression of steps. The flow chart's evident of that. It can be used to qualify the model as being appropriate, or also this process can be used to disqualify a model as being appropriate, either your own model or somebody else's. So it's a very effective step. Now, there's really no requirements for how you're supposed to document something, but it really depends on the requirements of the user, or that is the AHJ, project stakeholders. Maybe you have internal procedures for documenting things. Other authorities might have requirements as well. So there's really no one set way that the engineering guide talks about documenting things. It could be something as simple as a checklist that you perform to make sure you follow the proper steps. Maybe it's a project report, maybe it's the appendix to a report, or maybe it's a formal report or a presentation to an authority having jurisdiction, or maybe just something internally filed for your use in time. But again, it's a self-documenting process, and it definitely is something that is worth doing just to justify your own actions and to be sure that the model you have chosen is appropriate for use. That pretty much wraps up our intended discussion. We are definitely willing to answer some questions if anybody has any.
Back here.
Hi.
It seems to me that you're doing a problem that has a plume and entrainment, and you're collecting the gases at the ceiling in a layer. That's the basic problem you're solving. Is that true?
For most atrium analyses, that is true, yes.
That is true. So it seems that the key ingredient then is the entrainment that you get, whether you have a balcony spill plume or a fire in the center someplace, that's key. So what I don't understand is why would you dismiss algebraic models, particularly when the NRC said that they're just as good and sometimes not better, because they've been correlated against data that give you the exact results to the degree of accuracy with the data for entrainment in an equation. Yet when you use a code like FDS, you got to select the grid size. And the question now is how good is that entrainment with the grid size you've chosen? I mean, I think those are underlying issues that, should be addressed.
Those are good questions, and I'm going to actually refer to Craig for some of that, but I know off the top of my head, The main reason FDS was chosen wasn't really as a dismissal of all other reasons. It was because of the complexity of the project. The complexity of all the spaces interacting together couldn't easily be handled by the individual hand calculations. I know Craig was actually involved in the modeling project, so I'll let you speak more towards that.
Yeah, I certainly don't think we did not dismiss the algebraic equations. In fact, we went through that analysis up front. We're not convinced, based on reviewing what data the algebraic equations were based on, that this configuration of atrium matched with that. In fact, the algebraic equations in this case gave a lower exhaust rate than what we ultimately ended up with based on FDS. At the end of the day, we felt that was appropriate. Yeah. Yeah.
Then how do you check FDS? You have to check it against that data to make sure it can at least reproduce that data.
Okay.
So if you don't have that check, then how do you know? I mean, you have a complex space, yes, but what is the complex space doing for you? It's just throwing error into the blooms. I mean, again, if you don't believe any of these, do a scale model.
Right. Right.
I'm just looking at the approach. I mean,
yep.
You said you dismissed these things, and the nuclear thing, they didn't dismiss it.
Yeah.
You put them all on the same table.
Well, I think it's unfair to say we dismissed it, because we definitely went through that process. We chose not to use those results based on the entire modeling analysis. Like I said, we did do the algebraic equations. We did use FDS as well. At the end of the day, I think it was our opinion that the type of configuration of space, because of all the obstructions to smoke movement, didn't match what the testing and the data that the algebraic equations were based on.
All right. Thank you very much.